Okay, so going back to the example we just went over, namely the example 1.3.3, we can observe a couple things. So we uh, found that the supremum or the least upper bound was 1 for the set A, and we gave some indications that the 0 is going to be the infimum. Okay, so so we have two numbers. One corresponding to the supremum, which is 1, and 1 happened to be inside the set A, while 0, again, we have not rigorously proved that 0 is the infimum, but we basically gave the whole argument, just missing a couple of things. But 0 is not in the set A. So the important thing to notice here now, and this is what's going to motivate the introduction of the notion of maximum and minimum. So whenever supremum belongs to the set, we can actually call it a maximum, and when the infimum belongs to the set, we'll call it a minimum. Okay, so uh, and since both things can happen, whether the supremum may belong to the set or may not belong to the set, and then it makes sense to give a name or to do some notation in the case that this does happen. I mean, if this were always the case, then wouldn't be any need to introduce additional notation. Okay, so but it is important to make the distinction between maximum and supremum. And because of that, so it will be useful to introduce that notation. So the starting point here is that from example 1.3.3, we can see that supremum of A and the infimum of a set A may or may not belong to the set A in question. So both things can happen. I mean, the infimum or the supremum, it doesn't matter. They may belong or may not belong to the set. So both things can happen, and when they belong to the set, then we'll be saying that they correspond to a maximum or a minimum. So the definition here, definition 1.3.4, says that a real number A naught is the maximum of the set A if A naught is an element of A and A naught is an upper bound. An upper bound for A. Similarly, a number A1 is a minimum of A if A1 belongs to the set A and A1 is a lower bound, and A1 is a lower bound for the set A. In other words, what we have is that A to the a number A is a maximum of A if A happens to be equal to the supremum of A, and this number, supremum of A, is in the set A. Also, a number, the same way we can define, we can summarize what's above by saying that number A will be a minimum A if A is equal to the infimum of A, which is in A as well. So a set that contains its supremum has a maximum, and that maximum is a supremum. And a set that contains its infimum has a minimum, and that infimum is the minimum. From here, well, the notation we use is the maximum of the set A for the maximum of A. And here we use the notation, we denote min A the minimum of A. Okay, so now all notation introduced and all the, the concept of maximum and minimum having been defined, we move on to an example in the book. So the example is example 1.3.5. So we're going to consider two intervals. Consider the open interval 0, 2. This is something you're very familiar with. Then the interval 0, 2, in case, in the unlikely case you have forgotten what it is the set consisting of all the real numbers such that x is in between, so all the numbers x in the real numbers, such that x is in between 0 and 2, strictly greater than 0 and strictly smaller than 2. And we also consider the closed interval which is the set of real numbers such that x is greater than or equal to 0 and less than or equal to 2. So what is the difference here? Well, the set on the bottom, so the closed interval, contains both 0 and 2. So how do we know? I mean, just a quick reminder of what this way of defining sets actually says. In order to test whether a number belongs to the set, we need to see if the proposition here inside the brackets is satisfied. So here, after we enter this property, we need to check whether it's satisfied or not. We see, okay, is 0 greater than or equal to 0? Yes. And is less than or equal to 2? For sure. So 0 belongs to the set. This would actually fail here if we were asked ourselves, does 0 belong to the set? No, because 0 is not greater than 0. A number is not greater than itself. And so that means that the 0 doesn't belong to the set and 2 doesn't belong to the set. Of course, you're already very used to this notation, and you probably have used the open intervals and closed intervals in the past. But if we are actually just looking at the rigorous definition of that set, we would need to check in principle that whether or not 0 and 2 belong to these sets. It so happens that in the first for the open interval, the endpoints don't belong to the set, and when you define the closed intervals, they actually belong to the set because you're allowing for this equal sign here and here. So when you check the property for 0 and 2, it passes the test. It passes the test allows it to belong to the set. Allows us to say that it belongs to the set. So either 0 or 2. And so the thing I wanted to mention with respect to this is as it relates to the notions of minimum and maximum is, I mean, the first observation. So the supremum and the infimum for both sets are the same. So first of all, let's try to see that both sets, I mean, let's try to notice that both sets are bounded above and below and the important thing is by the same numbers. This is very important. The same numbers. And since they have the same upper and lower bounds, they have the same least and least upper bound and same greatest lower bound. So furthermore, or for these reasons, in fact, it's a consequence of this. For this reason, they have the same supremum and infimum. Okay, so far everything is the same for both sets. And what I mean, but before continuing, what are this supremum and infimum? The supremum in this case is 2, and the infimum is the number 0. So, but the interval, the difference here, what is the difference? The closed interval has a minimum and a maximum, while the open interval has neither. You see, because 0 and 2, as we just discussed, 0 belongs to this closed interval in 2 as well, right? So because we include the endpoints when we consider a closed interval, then both 0 and 2 are the maximum and minimum. And the open interval, on the other hand, does not contain the endpoints, which are the supremum and maximum. Okay, that's the difference between the two sets. And the main takeaway from here is that a maximum is a very specific type of upper bound. For it to be a maximum, it is required that it is an element in the set. And of course, the 0 and 2 are not elements in the set, so a maximum and an infimum are not going to be in the set. And more importantly, perhaps, I mean, you should not confuse the fact that a supremum exists with the fact that a maximum exists. If a maximum exists, then the supremum exists, but not the other way around. So an important remark is that if a maximum exists, then the supremum exists. from the examples above, it can be seen though that a set may have a supremum but not a maximum. Okay, so maximum means that there's a supremum, and in fact that supremum belongs to the set. So that's the way you have to think about it, and the same way for the least upper, the greatest lower bound, namely the infimum. And so now the next point is to go back a little bit to the beginning of the course and consider and revisiting the discussion surrounding the what the square root of 2 should be. It turns out that now that R is complete, so it satisfies the least upper bound property, we will be able to find a number that will correspond to the square root of 2. That means that there's a number such that R squared is equal to 2. And so and that's a very important thing. See, even though in principle solving an equation or not is an algebraic thing, in order to introduce a number system that will include a solution to this algebraic equation, we need to resort to topological considerations, and so this is a different kind of property we're after in order to extend the rational numbers, so that we're able to include solutions to the equation R squared is equal to 2. And this is the next point we're gonna make. I mean, we're not gonna actually prove that the square root of 2 actually exists at this point, but it should be natural from what our discussion with how we're gonna proceed in later on. And I mean, it should come as no surprise that we've defined in all of the examples we use. I mean, in many of the examples we used in before, we used for cuts, we used the cut as to be the set of rational numbers that were whose squares were less than 2 union the negative numbers. Now, I mean, if we just look at the set of rational numbers whose squares are less than 2, it's going to be a bounded set. We're going to show that. And since it's a bounded set, what can we say? Well, now that we know the real numbers satisfy the least upper bound property, then that set will have a least upper bound. The least upper bound will have necessarily to satisfy that its squared is equal to 2. Okay, so that's the point. Okay, and so we'll prepare ourselves to complete the proof that that's actually the case in a little while. So let's discuss things in the next video.